cloth does indeed date back to the time of Christ, and with artificial intelligence having something to say about the shroud as well.
Ever since the shroud first really appears in history, there's been controversy about it, and there have been questions about its authenticity.
It's religion and science living together on the same piece of cloth.
For over 700 years, the Shroud of Turin kept it secret. Now, artificial intelligence may have just exposed it. For centuries, the Shroud of Turin has been one of the most debated artifacts in human history. Some believe it is the burial cloth of Jesus Christ. Others argue it's a medieval forgery. But now, researchers have applied artificial intelligence to high-resolution scans of the cloth, and what the system detected is raising new questions that neither historians nor scientists can easily answer. Watch until the end, because the final detail AI uncovered might change how you see this artifact forever. The ancient mystery that refuses to die. The Shroud of Turin measures approximately 14.5 feet long by 3.58 feet wide. It sits protected in a cathedral in Turin, Italy, and contains one of the most puzzling images ever studied by science. On this ancient linen cloth appears a faint image of a crucified man, complete with wounds that match historical accounts of Roman crucifixion. What makes this cloth truly remarkable is that nobody can definitively explain how the image got there. For over a century, researchers have examined every inch of this fabric using the most advanced tools available. They have tested it, photographed it, analyzed it at microscopic levels, and still the mystery deepens. Many believe this cloth wrapped the body of Jesus Christ after his crucifixion. Others insist it must be a medieval forgery. The debate has raged for generations, with passionate arguments on both sides, but recent developments involving artificial intelligence are adding entirely new dimensions to this ancient puzzle. The shroud first appeared in documented history in the 1350s in France. Since then, it has survived fires, wars, and countless attempts to prove or disprove its authenticity. Each new scientific technique applied to the shroud seems to reveal more questions than answers. The carbon dating controversy that started it all. In 1988, scientists performed radiocarbon dating tests on a small sample of the shroud. The results suggested the linen dated from 1260 to 1390 AD, placing it firmly in the medieval period. For many skeptics, this seemed to settle the debate once and for all. The shroud appeared to be a clever medieval creation, not an ancient relic. However, researchers quickly challenged these findings. They pointed out potential problems with the testing methodology. The sample might have come from a repaired section of the cloth rather than the original fabric. Medieval nuns had repaired fire damage to the shroud, possibly using different materials. If the tested sample came from one of these repairs, the date would be completely wrong. Recent studies using different dating techniques have produced dramatically different results. Dr. Liberato De Caro, from Italy's Institute of Crystallography, developed a new method called wide-angle X-ray scattering. This technique measures how cellulose in linen fibers breaks down over time. When applied to the shroud, the results suggested the cloth could be approximately 2,000 years old. The X-ray testing compared the shroud's cellulose degradation with authenticated 1st-century linen samples from Masada, dated between 55 and 74 AD. The patterns matched closely, contradicting the 1988 radiocarbon results. This has reignited the entire authenticity debate with renewed intensity. The photographic negative nobody expected. In 1898, Italian photographer Secondo Pia took the first photographs of the shroud. When he developed the negatives in his darkroom, he nearly dropped the glass plates in shock. The photographic negative revealed a clear, detailed positive image of a man's face and body. This meant the image on the shroud itself was already a negative. Think about what this implies. Photography was not invented until the 1800s. The concept of photographic negatives did not exist in medieval times. How could a medieval forger create a perfect negative image without understanding the principles of photography? This question has stumped researchers for over a century. The image shows remarkable anatomical detail. Facial features, musculature, and wound patterns all appear clearly when the negative is reversed. No paint, dye, or pigment has been found on the cloth that could explain the image. The coloration exists only on the very surface of the linen fibers, penetrating less than a few microns deep. This superficial nature of the image eliminates most conventional artistic techniques. Paint would penetrate deeper into the fabric. Heat or scorch marks would affect more layers of material. The precision and subtlety of the image formation remains unexplained by any known medieval artistic method. The three-dimensional secret hidden in plain sight. In 1976, scientists John Jackson and Eric Jumper made a discovery that would change shroud research forever. They examined a photograph of the shroud using a device called the VP8 image analyzer. This analog computer was designed to convert brightness variations in images into height information, creating three-dimensional relief maps. When normal photographs or paintings are processed through the VP8, they produce distorted, meaningless results. This happens because regular images do not contain actual spatial depth information encoded in their brightness patterns. Shadows and artistic shading techniques do not correspond to real three-dimensional distances. However, when Jackson and Jumper processed the shroud image through the VP8, something extraordinary happened. The device produced a perfect, anatomically correct three-dimensional relief of a human body. The result was not distorted or warped. Every feature appeared in proper proportion and depth. Peter Schumacher, the inventor of the VP8 image analyzer, later described his astonishment when shown the results. He had never seen anything like it before or since. The shroud image contained encoded three-dimensional information that corresponded precisely to the distance between the cloth and the body it had covered. How distance became darkness. The VP8 analysis revealed an incredible property of the shroud image. The intensity of the coloration directly correlates with the distance the cloth would have been from the underlying body. Where the cloth touched prominent features like the tip of the nose or cheekbones, the image appears darker. Where the cloth hung farther away, such as over the eye sockets or neck, the image appears lighter. This three-dimensional encoding follows a precise mathematical relationship. The darker parts of the image on the linen correspond to the body surface areas closest to the cloth. The white or lighter parts represent areas where the cloth was furthest from the body. This inverse correlation creates what researchers call a cloth-to-body distance map that can be expressed as a single global function. When researchers at Sandia Laboratories first put the 1931 Henry photograph into the VP8, they could rotate the resulting three-dimensional image without any distortion appearing. The facial features maintained proper proportions from every angle. The arms, legs, and chest all contoured correctly in three-dimensional space. This coherent rotation proved the depth information was genuine, not an artifact of the imaging process. The VP8 image analyzer works by mapping brightness variations within video images into isometric projections. It essentially reads the intensity of each pixel and assigns it a height value on a display monitor. For the shroud, this created elevation maps showing the nose as the highest point on the face, with features like eye sockets appearing as proper depressions. The system revealed anatomical details that would be impossible to encode intentionally without modern computers. This discovery has profound implications. It suggests the image was not created by contact alone. Some kind of imaging process must have projected information about distance onto the cloth. The mechanism would need to work equally well for areas in direct contact and areas separated by air gaps of varying distances. Researchers have attempted to replicate this three-dimensional encoding using various techniques. Chemical contact methods fail at the microscopic level because they cannot create the gradual intensity variations needed to encode distance. Paint or powder applications cannot explain the superficial nature of the coloration or the precise distance correlations. Heat-based approaches produce images that penetrate too deeply into the fabric and lack the required intensity variations. The three-dimensional property eliminates photography as a possible medieval forgery technique. Even if someone in the Middle Ages somehow understood photographic principles centuries before their invention, they could not have encoded spatial depth information into a photograph. This property appears to be unique to the Shroud and remains unexplained by conventional imaging methods. Jackson and Jumper's detailed 1984 study demonstrated that the frontal image is consistent with a body shape covered with a naturally draping cloth. The image shading can be derived from a single global mapping function of the distance between the two surfaces. This level of mathematical precision would require knowledge of advanced physics and computational methods completely unavailable in medieval times. Enter artificial intelligence. Fast forward to recent years, and artificial intelligence has opened entirely new ways to analyze the Shroud. Dr. Thomas McAvoy, a professor emeritus of chemical engineering at the University of Maryland, applied sophisticated AI techniques to high-resolution photographs of the cloth. His research, published in June 2025 in the International Journal of Archaeology, revealed patterns that human observers had never detected. McAvoy used a technique called Principal Component Analysis, or PCA. This AI method can process enormous amounts of image data and identify the most significant patterns hidden within. The technique works by reducing the dimensionality of complex data while preserving the most important information. Think of it as finding the underlying structure in what appears to be chaos. When McAvoy applied PCA to visible light images of the Shroud, he discovered something remarkable. Almost all information in the Shroud images collapses onto a single component that mirrors raw pixel intensity. Specifically, the first principal component explained an astonishing 98.4% of the variance in the Shroud photographs. This means the brightness variations contain virtually all the important data. The AI analysis used photographs converted into the CIE lab color space, where the L dimension represents image intensity independent of color. For the Shroud, this intensity dimension proved to be the key variable capturing nearly all meaningful information. The second and third principal components contributed only 1.6% of the total variance, demonstrating how extraordinarily simple yet profound the image structure truly is. When McAvoy's AI differentiated this intensity map mathematically, it produced a height relief effect identical to the three-dimensional models created by the VP8 analyzer decades earlier. The AI calculated discrete approximations to the intensity gradient in the vertical direction, mimicking how the VP8's electron beam would scan the image. The resulting gradient image showed the same anatomical features and depth information. This confirms that the depth information is intrinsic to the cloth's image, rather than being artifacts of photography or processing. The AI essentially rediscovered the three-dimensional encoding through pure mathematical analysis, without any prior assumptions about what it should find. This independent verification, using completely different technology, validates the original VP8 findings. McAvoy's work represents a significant advance because machine learning algorithms can detect subtle patterns that escape human perception. The AI doesn't bring preconceptions or biases to the analysis. It simply processes numerical data and reports what the mathematics reveals. When that mathematics consistently points to encoded three-dimensional information, the findings become difficult to dismiss. The fact that two completely different technologies separated by nearly 50 years both detect the same three-dimensional properties strengthens the case that this encoding is real and fundamental to the image. The VP8 used analog electronics and cathode ray tube displays. McAvoy's analysis used digital computers and sophisticated statistical algorithms. Yet both reached identical conclusions about the cloth-to-body distance correlations. Ultraviolet secrets revealed. Perhaps even more intriguing are the AI findings from ultraviolet fluorescence imaging. In 1978, the Shroud of Turin research project conducted extensive scientific testing on the cloth. They photographed the shroud under ultraviolet light, which causes certain materials to fluoresce or glow in visible wavelengths. Vernon Miller served as the official scientific photographer for this historic examination. Dr. McAvoy's AI analysis of these UV fluorescence images revealed that the shroud exhibits very unusual properties. The fluorescence intensity varies significantly across different regions of the cloth in non-random patterns. Surprisingly, the right side of the shroud fluoresces more strongly than the left side. This asymmetry cannot be explained by natural aging or environmental factors alone. Similarly, the dorsal image on the back shows stronger fluorescence than the frontal image, where direct comparisons can be made. Near the feet, the backside fluoresces more intensely than the corresponding front areas. The pattern extends throughout the cloth in ways that suggest systematic rather than random variation. Using PCA on 21 ultraviolet-induced fluorescence images, McAvoy found that over 96% of the variation in all these images could be explained by their first principal component, similar to the visible light results. This PC1 was very highly correlated with the UV-IF intensity itself, meaning brightness variations again contain nearly all the meaningful information. The center of the shroud image fluoresces more strongly than areas near the head or feet. This gradient of fluorescence intensity suggests molecular differences across the cloth's surface. Such differences indicate that something affected the linen's molecular structure in position-dependent ways. These variations indicate differences in the molecular structure or chemical composition of the linen at different locations. Such differences could result from several factors including molecular bonding variations, contamination, or exposure to different environmental conditions over centuries. However, one possibility stands out as particularly intriguing given the other evidence. The pattern of fluorescence variation is consistent with exposure to some form of radiation. Different parts of the cloth might have received different doses or intensities of radiative energy, leaving permanent traces in the molecular structure of the linen fibers. The fact that these variations follow systematic patterns rather than random distributions suggests they originated from a single event or process. Miller's photography used ultraviolet lamps that did not evenly illuminate the shroud sections being photographed. This created a challenge for analysis because comparing fluorescence intensity between images required accounting for the varying illumination. McAvoy developed methods to overcome this problem by locating the center of UV illumination in each image and making appropriate corrections. The ultraviolet fluorescence results provide spectral evidence confirming what the PCA analysis revealed. Fluorescence spectroscopy data from the 1978 STIRP study shows that fluorescence intensity does indeed vary with position on the shroud. The combined photographic and spectral results demonstrate that molecular properties differ across the cloth in measurable ways. Charred shroud material collected during the 2002 cleaning could potentially be tested for evidence of neutron radiation exposure. Such testing would be completely non-destructive to the shroud itself and might help determine whether radiation played a role in the image formation or molecular variations. The radiation hypothesis. Multiple researchers have proposed that radiation played a role in creating the shroud image. The AI findings add significant weight to these theories. The superficial nature of the image, the three-dimensional encoding, the molecular variations revealed by UV analysis, and the threshold-dependent coloration all point toward a radiative imaging process. Several types of radiation have been proposed as candidates. Ultraviolet radiation could alter the cellulose structure of linen in ways that produce the observed yellowing coloration. The process would involve oxidative degradation of the outermost layers of individual fibers, creating the characteristic superficial discoloration seen on the shroud. X-rays or neutron radiation might affect the molecular bonding in specific patterns. Neutron radiation is particularly interesting because neutrons can transform carbon-14 into carbon-12 through nuclear reactions. If a burst of neutron radiation occurred, it could simultaneously create the image and alter the radiocarbon dating signature, potentially explaining why the 1988 tests gave medieval dates for a potentially ancient cloth. Corona discharge, a type of electrical phenomenon, could cause similar effects through electron radiation. Italian researcher Giulio Fanti has conducted extensive experiments on corona discharge mechanisms. These experiments show that intense electric fields can create surface coloration on linen that shares some characteristics with the shroud image. Italian researchers at the National Agency for New Technologies, Energy and Sustainable Development conducted groundbreaking experiments using excimer lasers. Paolo Di Lazzaro and his team at the ENEA Research Center in Frascati spent 5 years irradiating linen fabrics with ultraviolet laser pulses, seeking to reproduce the shroud's microscopic complexity. They used ARF excimer lasers emitting radiation at 193 nanometers in the deep ultraviolet range. They found that brief, intense bursts of this wavelength could reproduce remarkable characteristics of the shroud image. The laser-induced coloration was superficial, affecting only the outermost layers of linen fibers just like the shroud. It showed the same kind of yellowing and reduced fluorescence. The ENEA team achieved coloration depths of less than 1 micrometer, matching the incredibly thin discoloration observed on actual shroud fibers. Individual yellowed fibers appeared next to completely uncolored fibers, exactly as seen on the shroud. The colored region was limited to the crown of threads, with no penetration into the fiber core. Most remarkably, the researchers discovered latent coloration effects. Some laser irradiations that initially produced no visible change caused yellowing to appear gradually over months or even a year of aging. This suggests a two-phase formation process involving initial molecular modification followed by gradual oxidative manifestation over time. However, the researchers also discovered a significant limitation. The total radiation power required to color a linen surface the size of a human body would be enormous. They calculated that achieving shroud-like coloration would require ultraviolet light, exceeding the maximum power released by all ultraviolet light sources available today. The process would demand pulses having durations shorter than 1/40 of a second, and intensities on the order of several billion watts per square centimeter. These represent energy levels far beyond anything available in medieval times or even most modern laboratories. Whatever created the original image would have required an energy source of extraordinary power and precision. Dr. Di Lazzaro stated clearly that reproducing all the main physical and chemical characteristics of the shroud image is very difficult, almost impossible, even with today's technology. This makes it extremely unlikely that a medieval forger could have created the image using any technology available in that era. What the AI cannot explain. Despite all these technological advances, fundamental questions remain unanswered. The AI can detect patterns and correlations with unprecedented precision, but it cannot explain the underlying mechanism that created the image. No known natural process or artistic technique can account for all the observed properties simultaneously. The image formation mechanism must satisfy multiple stringent constraints. It must work on the outermost surface of individual linen fibers without penetrating deeper than a few microns. It must encode accurate three-dimensional spatial information into a two-dimensional surface in ways that survive for centuries. It must create a perfect photographic negative without using photographic techniques or understanding photographic principles. The mechanism must affect the molecular structure of the linen in ways that show up under ultraviolet analysis as systematic variations in fluorescence intensity. It must produce coloration that results from oxidative degradation rather than applied substances. It must create images where no directionality can be detected in the coloration of individual fibers. Attempts to replicate the shroud using medieval materials and techniques have consistently failed to reproduce all these characteristics together. Researchers have tested direct contact with bodies, bas-reliefs, heated statues, chemical vapors, and countless other methods. All fail at one level or another when examined in detail. Modern attempts using advanced technology have also fallen short of complete replication. Chemical contact methods work at the macroscopic level but fail under microscopic examination. The fiber-to-fiber variations and the superficial nature of coloration cannot be achieved through contact with substances. Radiation-based approaches can reproduce some features but require unrealistic energy levels for full-body imaging. The ENEA experiments showed this clearly. While they could color small areas of linen, scaling up to body-size dimensions would require power sources that don't exist. The AI analysis strengthens the conclusion that radiation was likely involved, but it cannot identify the specific type or source of that radiation. Machine learning algorithms can recognize patterns and correlations in existing data, but they cannot extrapolate to mechanisms completely outside the training data or known physical processes. McAvoy's research demonstrates that the vast majority of information in both visible and ultraviolet images is contained in intensity variations. The AI can parse these variations mathematically and extract three-dimensional information, but the question of how that information was encoded into the cloth in the first place remains beyond the AI's analytical capabilities. The ultraviolet fluorescence variations suggest molecular differences consistent with radiation exposure. The PCA can identify and quantify these differences, but determining whether they resulted from neutron radiation, ultraviolet radiation, corona discharge, or some completely unknown process requires additional experimental evidence and testing methods. One particularly puzzling aspect is the precision and uniformity of the imaging process. If radiation created the image, it must have acted from all directions simultaneously or in rapid succession to create the observed even coloration. The image shows no preferred directionality that would suggest radiation from a single source or angle. The blood evidence. Separate from the body image, the shroud contains numerous blood stains that have been extensively analyzed. These stains show properties consistent with genuine human blood and were transferred to the cloth through a completely different process than the body image. The blood appears to have been on the cloth before the body image formed, based on the observation that no body image appears underneath the blood stains. Recent microscopic analysis has identified particles of creatinine and ferritin within the blood samples. These compounds are typically found in the blood of people who have experienced severe trauma and muscle breakdown. Creatinine levels increase dramatically when muscles undergo extreme stress or damage. Ferritin, an iron storage protein, appears in high concentrations in cases of severe polytrauma. The combination of creatinine bonded with small nanoparticles of iron oxide creates a peculiar structure. This specific arrangement occurs in human organisms during cases of violent multiple traumas, such as torture. The presence of these biological nanoparticles points strongly to a violent death for the person wrapped in the shroud. However, it's important to note that a 2017 study making these claims was later retracted in 2018 due to concerns about validity and reproducibility. The journal editors stated there were insufficient controls to support conclusions about human blood or physical trauma. Despite this retraction, some researchers continue to reference these findings, though the scientific community remains divided on their validity. The bloodstain patterns also correspond with specific types of wounds observed on the image. Flow patterns match what would occur from bleeding while in an upright position, and then horizontal. Blood flows according to gravity, and the patterns on the shroud show this clearly. Stains around the head area show the characteristic pattern of blood flowing from multiple puncture wounds, consistent with a crown or cap of thorns pressed into the scalp. Wrist and foot areas show blood flow patterns matching crucifixion wounds. Contrary to popular artistic depictions showing nails through the palms, the shroud shows wrist wounds. Medical studies confirm that wrist wounds could support body weight during crucifixion, while palm wounds could not. This anatomical accuracy suggests knowledge beyond what medieval artists typically possessed. A prominent stain on the right side of the torso corresponds to a post-mortem wound, consistent with the biblical account of a spear thrust after death. The fluid surrounding this wound shows properties suggesting a mixture of blood and another fluid, possibly the blood and water described in the Gospel of John. AI analysis has been applied to the blood evidence as well. Pattern recognition algorithms trained on medical imaging and forensic data have confirmed that the bloodstains show expected characteristics of contact with actual wounds rather than being painted or applied artificially. The flow patterns follow physical laws of fluid dynamics and gravity. The three-dimensional body image and the two-dimensional bloodstains appear to have been created by completely different processes. Blood was transferred through direct contact with wounds, leaving stains that penetrate into the fabric and show clear directionality. The body image, by contrast, has no directionality at the fiber level and exists only on the surface. Chemical testing by the 1978 STIRP team identified hemoglobin and gave positive tests for serum albumin. These are components of real blood, not paint or dye. The tests eliminated pigments as explanations for the blood marks. However, the reddish color of the bloodstains after so many centuries remains puzzling, as old blood typically turns brown or black over time. Pollen and botanical clues. AI and microscopic analysis of the Shroud of Turin have examined pollen trapped in its fibers, revealing geographic patterns. In the 1970s, Swiss botanist Max Frei Sulzer identified Middle Eastern species. Later, Israeli botanist Avinoam Danin highlighted key plants like Gundelia tournefortii and Zygophyllum dumosum, which coexist only near Jerusalem and surrounding regions. Several identified plants bloom in March to April, aligning with Passover season. Additional pollen matches Mediterranean routes into Europe, suggesting a historical journey. While over 50 species reduce the likelihood of random contamination, critics question sampling methods and note missing expected pollens like olive. Machine learning confirms many identifications, but underscores the need for new, independently verified testing. The molecular mystery. AI analysis of the Shroud of Turin using ultraviolet fluorescence revealed organized molecular variations in the linen that natural aging alone cannot explain. CIE lab analysis showed over 96% of differences come from brightness, not color, meaning structural changes drive the data. Patterns align with the body image rather than random contamination or environmental exposure. Burn marks from the 1532 fire show distinct chemical signatures, separating heat damage from image areas. Fluorescence asymmetry between left and right and front and back images suggests the image formation process itself affected the cloth. Some propose neutron radiation as a cause, potentially altering carbon-14 and affecting 1988 dating results, though this theory faces major physical challenges. Spectroscopic data from the 1978 Shroud of Turin research project and advanced X-ray scattering further confirm systematic molecular differences requiring explanation. Comparing medieval art. Researchers have used AI to compare the Shroud of Turin with 13th to 14th century medieval art. Machine learning trained on thousands of artworks finds major differences. Typical medieval pigments, binders, brush strokes, and application patterns are absent. The shroud shows no directionality, no binders, and only superficial fiber coloration, unlike medieval painting methods. Anatomically, The image is unusually accurate for its era, including wrist wounds instead of palm placements common in crucifixion art. There are no underdrawings, no stylistic fingerprints, and no edge buildup typical of applied pigments. AI analysis also highlights the image's photographic negative quality, something unknown in medieval times, placing it outside the statistical patterns of known medieval artwork. The Shroud of Turin continues to challenge our understanding, and artificial intelligence has revealed patterns that deepen rather than solve the mystery. From three-dimensional encoding to molecular variations, suggesting radiation exposure, the evidence points toward image formation mechanisms that science cannot fully explain. The cloth remains what it has always been, an artifact that invites questions rather than providing easy answers. What do you think explains these AI discoveries on the Shroud? Share your thoughts in the comments below.